Hello everyone, my name is Kyle, and today we're going to be creating this cool quaternion interpolation effect, say that 3 times fast, over some geometry. We're going to explore how to create quaternions with matrices, and then we're going to use the fancy slerp function to interpolate between these orient attributes. At the very end, we're going to cover some basic vex Falloff techniques that I use often in my setups. So it should be a fun one, and let's jump into it. Okay, first thing first, we need to drop a geometry container. And the first thing we want to do is build out that kind of leaf petal model that I had in the initial render. So let's do that. Let's drop a line where we want to resample it. And I want to sweep this line. Let's use the ribbon as the second input. And then shape this using the channel ramp here. And I think I'm going to turn these into B-splines. And of course, you could edit how this petal looks for as long as you need. I'm going to add some resolution to this guy. I'm also going to make my line shorter, maybe 0.5 here. Something more like this. And I was trying earlier in my test to kind of get rid of this curve. And maybe you can figure out how to do this, but initially I was trying this grid option, and you can lower the scale here and make it less round and stuff to try to get rid of this edge. But I was getting some weird topology with these joining lines at the tip. So for now, I'm just going to leave it off. Shape this a little more. Something like that. Maybe pinch it a little bit. Okay. Add one more point. Cool. And again, you could shape that forever, but I think this works for this tutorial. The next thing we want to do is poly extrude this. Push it out a little bit. And actually make sure back faces are on so we don't have reverse geometry. I'm going to output the back. And what I did for shading is I also exported this side. And you could separate that out into a different geometry container or just assign it a material for render time. Next, I want to subdivide everything. And this is how I was smoothing out the geometry. And it looks like we're getting pretty good topology and normals. There is like a little normal bump here at the bottom, so I'm just going to drop down a normal stop. Plug this in here. Can run over the vertices, and if we kind of change the slider, that smooths itself. So that's looking pretty good to me. One thing we can also do is add a bend deformer. We put this after the subdivide and just bend everything a little bit. Make sure it's going in both directions. Have it oriented in the wrong direction, in the correct direction. And I always screw this up. Okay, the correct setup is to have the up vector in X be 1 and the capture direction to be 1 if your incoming geometry is facing up and down. That seemed to give me what I want, and also make sure to have deform in both directions turned on. You could kind of bend it in and out like this. I'm going to decrease the poly extrude just a little bit, probably put this out like 125. Maybe decrease the height of the line as well a little bit, something like that. Okay, cool. So there's our little leaf petal thing. We could drop a null, call this in petal, and the initial modeling is done. So now we want to copy this onto some sort of geometry. I'm just going to use a torus for this example. Let's orient the torus in the z-axis here. Our points are going to need geometry and normals to be copied onto. So let's drop a normal stop and put it on points. If we visualize this, you can see the normals are facing away on the points. Next, we want to scatter some points onto the geometry. Let's just use 1,000 for now. We can change this later. So our points have inherited the normal. That's important. And next, what we need to use the slerp function is two orient attributes. And I think the easiest way to make orient attributes is through creating two different matrices and then converting those matrices into quaternions so you can slerp between them. So let's create those two matrices using a little bit of X. Drop down an attribute wrangle. And one thing we will need along with our normal attribute is an up attribute. So let's create that up attribute real quick. It's going to be v at up is equal to, and we'll just put it at 0, 1, 0. And then we need to do a cross product between our up and our normal attribute to create this kind of third axis for the matrix nomen. And I'll visualize this in a second. So let's do vector attribute out is equal a normalized cross product of v at n and capital N and v at up. If I visualize this and click on the out attribute, you can see we have our out attribute go in this direction. And if it's tough to visualize, you can always go in here and click on this out pencil and then decrease the length scale. So I'm going to do that here. We have our n attribute, which is going straight up. I'm going to do the same thing for n. And we have our up attribute. So you can see that we have, basis vectors for every single point. And this is what is going to create, each of these vectors is going to be put into a make transform function to create a matrix. So let's do that now. We want to create a 3 at m. 3 is the syntax to initialize a 3 by 3 matrix. And then we're going to use the function make transform, and we're going to feed it v at n, v at up, and v at out. So let's visualize this now. We could turn off these vectors and just look at m. And they should look like the same thing we just created. So now we have matrices on each point. But the slerp function requires two quaternions, not matrices. So what we need to do is convert this matrix into a quaternion, and we'll use that using the quaternion function. So p at orient is equal to quaternion of 3 at m. For now, let's get rid of the attribute visualization and just make this a local variable called m, and then change this to m. I think then it won't yell at me. Okay, it's still giving me errors, but I think it's working correctly. From what I understand, this is only a 3 by 3 matrix because it's just rotations, but if someone knows a little bit more vector math than I do, I'd love to know why this is giving me an error. It seems to be working correctly. Okay, so we can name this node create orient 1. But because the slerp function acts just like a normal lerp function, we need an orient 2 to lerp or slurp between. So let's just copy this node. And this time, before we convert it to a quaternion, I want to rotate this matrix by a certain amount. So the rotate function likes the rotate amount to be wrapped in a radians function. And then we'll just do channel float, call this spin. And then we're going to use vector attribute out. And this is the axis it's going to spin along. So let's do this. And as always, when we're using radians, you need to change the spin from negative 360 to 360. And let's do a copy to points and see what is actually going on. Okay, so this is our orient 2 here. And I'm going to pack these just so it runs a lot quicker. And if we spin this a little bit, you can kind of see what's going on. And currently, these are kind of oriented in the wrong direction, right? I'm going to turn off this M visualization. I want the pedal to be facing straight up and down, and right now it's kind of facing sideways. So you could change the orientation of the line, but I know we did some fancy stuff with the bend here, so I'm just going to use a transform stop at the very end. This probably isn't the cleanest way to do this, but it'll work for this. And I'm going to find the right transformation here to make everything align. So that seems to be almost doing the trick. I'm also just going to drop down another wrangle We can put this before the orients, and we're just going to call this p-scale, or init p-scale, initialize p-scale, and we're going to say f at p-scale is equal to channel float p-scale. Okay, so this is working correctly. So the orient attribute we're creating in this wrangle is driving the orientation of our copied points. And if we plug in this one, you can see there, let's make sure the p-scale is plugged in. Also oriented kind of in the same direction here. But we don't want them facing up like the second orient, we want them facing down. So let's rotate the first orient attribute using the same thing. Rotate m, radians, channel float, spin by v at out. Let's edit the parameter interface, spin -360 to 360, apply and accept. Let's plug this in here, check it, and just have these guys facing straight down. So our first orient is making the kind of scales and pedals face downward. The second orient is making them face upwards. And now all we need to do is use we've done all the heavy lifting, and we just need to use the slerp function to slerp between them. So let's drop an attribute copy. I need to get this orient attribute onto this stream. And you could do this by plugging it into the wrangle. I think this is a little bit easier. Let's copy an orient. And right now they're both orient, so let's make this orient 2. The copy to points naturally only reads the orient attribute. So you can see when I switch this to orient 2, it no longer reads the orient. So if you're debugging this and you're wondering why, why isn't my orient showing up? The copy to points only reads p at orient, not orient 2. So we're going to copy in over orient 2 into this stream, right? And if I select this, you can see I have orient 2 in my geometry spreadsheet and just a normal orient. If we middle mouse click, you can see we have orient and orient. How many times have I said orient in this video? I have no idea. And lastly, we want to use the slerp function, kind of the whole point of all of this effects. So p at orient is equal to slerp between our incoming orient, so p at orient, and p at orient 2. And I'm just going to move this by a channel float called a mount. And we'll switch this out later for a mask. Plug this in. And if I move this around, you can see kind of how cool this function is. Houdini is so cool. I just love being able to do this stuff. All right, so this is the slerp function. But obviously this movement is kind of lame, It's not very exciting. So before the p-scale here, let's create a mapped Falloff. So let's drop a wrangle. I'm going to use a little bit of Vex to create this. We want a map from 0 to 1 in the y direction on the torus. So let's first create that map. Vector bbox is equal to rel point bbox on the incoming geometry for v at p. And we're going to create a map based off of the y part of the bbox vector. If we visualize this, it's going from 0 to 1. Next, I want to create another wrangle, and we're going to fit this map between 0 and 1 to kind of create a moving transition. So we're going to need to bring in our map attribute. Let's do float map is equal to f at map. And then we're going to create a couple local variables here. Let's do float p is equal to channel float position. Float w is equal to channel float width. And I know we're going to need to fit p here, so let's just fit it currently. Fit 01 p from -w to 1. And we want to create this mask attribute. We're going to fit it map from p to p plus w from 0 to 1. And then we're going to shape it with the channel ramp. Mask equal channel ramp. Shape mask. And lastly, we just want to write it out to an attribute called mask. And it doesn't like something. I have 2 commas in there. So let's visualize this. And I'll make this code a little bit bigger if you want to just copy that down. So now if we visualize our mask attribute, you can see, we have this nice position slider. We could just kind of slide through it. So this is going to be create mask 1. I'll name this, actually, I'll give this a better name. We can do create mask for orient. And then I want to do another one for just the scale, for p scale. We'll use this later, but I'll just kind of leave it on the side for now. Okay. So I'm going to plug this into initialize p scale. Another thing we can do to make this fall off a little more interesting, and I'm going to animate it real quick from frame 1 to 72. Kind of give it a reverse S-curve. Something like that. One thing we could do to make this a little more interesting is add some noise to this initial map, so this transition is a little bit more broken off rather than just a linear transition. So let's do that real quick with an attribute bop. I'll name this create map. Let's jump inside. We're going to need a few things here. Let's grab an AA noise, a fit range, a ramp parameter, and a bind export. We'll also need, we will also need a bind import. It's going to be map. And let's wire this in. We're basically just making a noise to run over our points. So let's plug in noise here. Let's fit this from -0.5 to 0.5. Let's plug it into our ramp parameter, change it to spline, and multiply this against our map. And I'll bind export this to a float called just noise. And I'll also bind export this to our map attribute. So if I click this, I'm also going to jump back in and right click on the A noise, go to Vex and VOP options and do create input parameters. This will promote all the parameters to this level and make it easier to edit. So if we click on our map attribute now, we can see it's a little more broken up than what we had here. And we definitely want higher frequency. Maybe it clamped a little more. We can edit these settings in a second. But let's look back at our mask. Let's invert it. So you can see it's kind of growing on and then it folds together. And if we go to our slurp now, we're going to actually delete this channel float amount and put in ff mask. Okay, so now if I look at this copy to points and we go back to our, this is our mapped transition or orient. I'm renaming it again, I'm sorry. You can see that each piece is kind of rotating the way we want it to. I'm going to go into our orients and actually flip these around. I think I want the first one to be facing up and down, the second one to be rotated inward like that. And I'm also just going to go to our bend and flip this. So now if we kind of sweep through, they start facing upward and then they turn downward. But this noise is obviously, I think, in my mind, doing too much here. So let's kind of smooth this out so we have kind of a softer transition. Yeah, something like that. Now at this point, you could probably increase the scatter amount. So that's what I'm going to do. Let's increase this to like 5,000. And then on our P scale, we could decrease the slider. Right. Just to be a little fancy, what I'm going to do is actually multiply this by fid01 rand for every point number between 0.5 and 1, just to give it a little more variation, something like that. Maybe 0.75. Okay. Okay, then after the slurp, I'm going to multiply our p-scale again. And this is why we needed to create the second map. So I'm just going to copy this map transition. We can put it below this. And we want, so our orient, we kind of want looking like this, but our p-scale we want looking like this, right? Let's smooth out this mask attribute. I'm going to name this mask p-scale. I'm going to call this mask orient. I'm going to have to change in the slurp. We want this to be mask orient. And here we want to do f at p-scale times equals that mask p-scale. Cool. So now if I scrub through, they start low. Maybe I can shift this little ramp around a little bit. And you can see the effect that's happening. I think it looks pretty cool. You know. That's feeling really nice. And it fades off. So that's the basis of this effect, really. We're creating two orient attributes, and we're using a slurp function to slurp between those two orient functions. I think rendering is a bit beyond the scope of this tutorial, but the rendering was it was a really basic setup. I was just splitting out this extrude side I was talking about earlier and putting a different material on that and just using some large HDRIs to render stuff. But if you like this content, please consider subscribing. We just hit like 150 subscribers, and I'm super stoked that people are enjoying the content. So thank you very much. I hope to see you guys in the next tutorial, and I'll catch y'all later. Thanks.